In this video, I'm going to walk through my solution to the homework where we had to measure the scaling of read and write operations. This isn't the most efficient solution, it's just the one I came up with on the fly. So first I wrote down what the homework requirements were as stated in Blackboard. I imported a couple libraries, and then I started playing around with Faker to generate some random entries that I'll need for that large CSV. So I worked with name and emails and cities and all these different fields, and eventually I came up with a dictionary containing 10 different entries of various sizes. Some of these don't actually meet the requirements for the homework, so like day of month and bank, those don't actually meet the requirements for the homework, but assuming we can fit something in there that works on average, this is probably sufficient to balance out the sort of shortness of these. So that's just one row though. We actually want to create a data frame. So the next step that I took with that row of random entries was I put it into a data frame where I ignored the index. That did create a data frame with multiple rows, but it was all duplicates. And so I wanted something slightly more realistic for my data frame with random content. So what I decided to do was to create a function which makes a random row in the dictionary, and so then I can call that function within the loop to create a data frame where every row is unique. So that's the sort of output that I had in mind, and it sort of looks like a real CSV with relevant entries. The next thing that I want to do was, once I've got that pandas data frame, was to time how long it takes to create the CSV on disk. So here I'm using data frame to CSV, and it's telling what the file name should be. And above and below that I have a timer function. Basically, I start the clock and I then print what the elapsed time was by differencing the current time with the start time. And then I can use this OS path get size to figure out how many megabytes that data frame is as a CSV. Because this data frame only has 5 rows in it, it's only 686 bytes on disk. So then I played around with how many rows would I need to create that would actually create a 0.1 megabyte file. And so I found that that was 850 rows resulted in a 0.1 megabyte file. And if you look back at the initial requirements, that was the first file size that we wanted to get. Then I thought about how that would scale, in the sense that if 850 rows takes 6 seconds to generate, then that means when I make a lot of rows to get a very large file, it's going to take a really long time. So specifically, 850 rows gets you 0.1 megabytes. So then a 1 megabyte file would be 8,500 rows, and that would take about a minute. And if you do the math, you can find that a 500 megabyte file, if it grows linearly, would take about 9.5 hours or 10 hours. And so that's time that I don't really want to wait. So I'm going to have to come up with something else that's going to generate the data and be a little bit more efficient than waiting 10 hours for a 500 megabyte file to be created. Just to be clear, that's distinct from how much time it takes to write the data frame to disk. That's a much faster operation. The reason this takes a long time is because our function where we're creating the row is calling a random generator for each one of these entries, and that's a very expensive operation. So that's the thing that we want to avoid, is the creation of those many calls to a random function. So what I decided to do was play around with copying the data frame. So here I have an 850 rows of essentially random data, and I can create a copy of that data frame and then append it to the current data frame. So I'm going to run this cell. That'll take about 10 seconds. and then so 7 seconds in that case, and then I'm going to write it, and that's very fast. And if I look at the shape when I make a copy of that, it's 1700 rows. So that's the 850 rows of the original data frame copied twice to get us 1700 rows. And again, that takes a little bit longer to write to disk, but generates a 0.2 megabyte file. So exactly what we're hoping for, a larger file, taking not as much time to create. All right, the next thing that I needed to do was, once I figured out that concatenation method, I needed to build a appropriately sized data frame. So this loop is creating the initial data frame with 850 rows in it, and then I want to duplicate that 10 times. And so I'm basically creating a list. So 10 times of that original data frame will yield a 1 megabyte file. So let's correct this here. 100 copies of this original data frame will yield a 10 megabyte file, and then 5,000 copies of it will create a 500 megabyte file. So this is how we're going to get away with creating large data frames in memory without having to do that expensive operation of repeatedly calling the random faker library. Then we can sort of measure how long it takes. So that 8,500 row data frame only took 0.86 seconds to create, and then 0.2 seconds to write it to a CSV, and that resulting file is as what we desired, 1.0 megabytes on disk. So now that we sort of have the mechanics of the creation and writing down, we're actually going to create a function which will be able to create an arbitrary size data frame. And so that's what we're going to pass in. We're going to pass in how big we want it to be. Then we're going to create that many copies of it in memory. So the data frame that gets returned will have as many rows as it takes to get to however large we want. Looking back at the assignment, we have a set of sizes that we want to explore, and then for each of those sizes, we're going to test this 3 times, we're going to test that 3 times, test this 3 times. So the first thing that I did was I focused on just the right portion of the experiment. So I needed some dictionaries to store my results, and then I looped over those different file sizes here. That's the list of file sizes. So this is going to be iterating over 0.1, then 1, and 10, and so forth. And then I'm storing for each of the experiments, creating a list where I can store the time and file sizes that were actually created. And then this is my trial index, so it's going to be 0, 1, 2 in this case to give me 3 trials. So the first step within the specific trial and specific file size is to create that data frame of the appropriate size. And then I'm going to see how long does it take to write. And then the elapsed time is the difference between this time and after the write to disk portion. And then I can actually measure how big the file is in megabytes in this line. And then we're going to store those results to a list. Then after we've done the 3 trials, so this is 0, 1, 2, 3, so this list will have 3 elements in it, and this list will also have 3 elements in it. And then the average write time is just the sum of all those elements in the list divided by the number of trials. Once I've got the average values, then I can store those into a dictionary of average file size as the key and the average write time as the value. So that runs over the multiple sizes and gets us back an average execution time for the write operation. And I'm going to plot that using that dictionary with the keys and values as my x and y values for a scatter plot. So here we get a very straight linear curve of the file size, which is the input, and the write time, which is the output. So the next thing that I experimented with was I took that same code and I basically duplicated the list for writes and then made a copy and looked at the read times. So the complication here is that I took the original write test, copied that into basically the similar read test, and then separated those two with a bit of flushing the disk cache. Not that that is vital to this experiment, but I just wanted to have accurate results. Then I basically duplicated all the averaging operations for read and write, and then ran the test, and I'm gonna, Then we'll plot that, and we get back the write or read time in terms of the file size. So the read operations are much faster. To make this a little bit more clear, I'm going to reorder these and rerun that plot. There we go. So the read operations are faster than the write operations.